All right, welcome everybody to today's stream for PHYS 413 Quantum Mechanics 1 at Jacksonville University. Just a reminder, today is the last live stream for this class. We are nearing the end of the semester, so you're going to have next week to basically finish up your last assignments. Those are going to be due on April 20th. But like I said, today will be the last live stream for Quantum Mechanics 1. I've sent you an email earlier this week with information about office hours for next week. So you can see that. That's when I'll be available to you to chat about your your last couple of assignments, which I've already starting to get in. So I think folks are pretty much knowing what they are doing. So we have pretty much addressed all of the topics that we need to for this class. Folks seem to understand everything pretty well. So what I'd like to do today is do just a real qualitative introduction to the subfield of physics called solid state physics. Solid state is the study primarily of metals, conductors. It's the study of how electrons behave when you turn on an electric field, when you apply a voltage. And so solid state is really where you get all that Ohm's law stuff from, kind of at a fundamental level. And because solid state deals with electrons, because it deals with these particles that are small enough to be at the quantum mechanical scale, solid state is based on quantum mechanics. It's one of the most important applications of quantum mechanics. And so it's a nice way to end this class and just kind of recap and take a look at what we've talked about before. So here's the picture I want you to have in mind. Solid state, like I said, is the study of metals. So you know that a metal, being a solid, is going to be composed of atoms that are pretty stationary. So here we've got some atoms. I'm just going to put in the nuclei first. So each one of these positive charges is a nucleus. And we're going to assume that those are stationary. So the atoms themselves, we're going to assume, are pretty stationary. Right? You know that that temperature is the average kinetic energy of these things. They do vibrate a little bit, but they're really not moving much compared to the electrons. So around each of these atoms, you have these electrons floating around, right? Kind of this traditional picture of the atom. We know that it's a little more complicated than that because of these electron wave functions, but we're going to break this down into wave function in a second. The way it works in a metal is that most of these electrons are tightly bound. So for example, for this atom on the left here, these two electrons maybe are very tightly bound to the nucleus, and maybe these two electrons are tightly bound to the nucleus. Maybe these two are tightly bound, and maybe these two are tightly bound. Tightly bound meaning they're very far down in the energy levels. So remember our solution of the hydrogen atom. You have these energy levels that get stacked like this, and they get closer and closer together. So these electrons that are tightly bound, they're somewhere down here, right? It's going to take a whole lot of energy to get them to jump up, right? Whereas these electrons that are a bit more loosely bound, and that's usually 1 to 2 electrons per atom are loosely bound. Those electrons are somewhere up closer to the top, right? They don't have as strong a connection to the nucleus, and so it doesn't take a whole lot of energy to kick them out of that particular atom. Now, they don't fly out of the metal. I mean, they can fly out of the metal, right? That would be an electric spark, basically. But it doesn't take a whole lot of energy to get them to fly out of the atom and kind of move along the metal. And so these loosely bound electrons, we call those the valence electrons, right? So these valence electrons, they don't tend to stay near their atom. They kind of wander around the metal. So these valence electrons, they don't really belong to any particular metal or to any particular atom. They kind of move around the bulk of the material. And so they're kind of itinerant electrons. They don't really have a home atom. You know, they left their home atom a long time ago, and you know the odds of them getting back to it are very, very slim. What that means is we've got electrons that are basically moving around, kind of almost like free particles, except that they've got these atoms in the way, right? Because these atoms are slightly positive, right? So a neutral atom has the same number of protons and electrons, but we've ripped away one or two of these valence electrons. And so these atoms now have a slight positive charge, meaning that the electrons are going to be, as this electron comes by this atom, it's going to be a little bit attracted to it, but then it's going to be a little bit attracted to this one, it's going to be a little bit attracted to this one, going to be a little bit attracted to this one. And so we've got a potential energy set up where the electron is going to try to fall into each atom that it passes by. So that's where we finally get to a quantum mechanical picture. So let's imagine you are an electron. You're moving along the x-axis here. We're just going to stick with one-dimensional motion for now. It turns out this one-dimensional model works pretty well to describe a metal that really, I mean, you know by now that 3 dimensions is just 3 one-dimension problems smashed together. Here's the potential energy that it sees, right? It's moving along, and then it sees an atom, and it wants to get attracted to that atom. Then it sees another atom, wants to get attracted to that. Then there's another atom, then there's another atom, then there's another atom. And so each one of these cusps here goes like 1 over r, the Coulomb potential energy, right? So V equals K E squared over r that we worked with last time in the hydrogen atom. Well, now you've got a 1 over r for this atom, and a 1 over r for this atom, and a 1 over r for this atom, and a 1 over r for this atom. So in principle, you have an Avogadro's number of Ke squared over r's to worry about because you've got all these atoms spaced throughout the bulk. Now that's not a solvable problem, but it is easily approximated. One rough approximation we can make that actually works out really well. Instead of treating these things as cusps, we can actually just treat this thing as a set of rectangular wells. You remember working with this earlier in the semester, where you have these finite square wells. So instead of doing the Coulomb potential, we can do the finite square well. You remember doing this problem, the finite square well, where you've got an electron that doesn't have enough energy to get out, but it can tunnel through to the next side. Well, that's exactly what's going on here. The electron's moving along, it tunnels past this atom, etc. And so what you can do to model this, instead of having your exact, Coulomb potential, you can just have these, let me get another color here. You can just have these wells here, each separated by a distance a. So there's a distance a, there's a distance a, etc. So a is going to be your atom spacing. And this is a solid, so the atom spacing is fairly regular, especially in a metal that's just made of one element. This atom spacing is fairly regular. And so what we can do is simply treat this as a bunch of finite square wells. And so this is one of the most important applications of the finite square well. You might remember we talked about finite square well modeling quantum dots. Well, now it's modeling atoms as well. So each one of these wells here is an atom. So here's one atom. So here's an atom, and here's an atom, and here's an atom, and here's an atom, and here's an atom, because that's where the electron's going to tend to be attracted to. So the name for this model, it's got a fancy name called the linear combination of atomic orbitals, or LCAO, linear combination of atomic orbitals. The way this model works is you start with just one atom, right? So I said each one of those atoms is represented by a well, so you're really starting with just one well, right? So you've got your well here. You remember this problem, right? The width of the well is what's going to determine how many states the well has, how many bound states, right? We're not interested in scattering states because that would be an electron flying away from the metal, and we don't really have that happening too terribly much. So we're pretty sure we're going to be in a bound state. The most important state you're worried about is that lowest energy state. So here we call this the ground state energy, or EG, and our textbook uses superscripts for labels, so this is not E to the G, this just means energy of the ground state. So this G stands for ground state. We call it the ground state because you can't get any lower than this energy, right? So it's the ground of the energies, right? You can't get any lower than this. And then there might be more states. There probably are more states. So we can call this the first excited state. And there can be a whole bunch of excited states above this. So there can be a whole bunch of excited states above this, but primarily we're interested in this ground state over here. And so this is going to have associated with it a wave function, right? So I'm going to be able to say that H acting on the energy eigenstate of the ground state, the ground eigenstate, I guess, is going to equal Eg times phi g. So again, this Hamiltonian here is the Hamiltonian operator. We're acting on the state here. It spits out the same state with the energy eigenvalue here. Okay, so yeah, and you know how to work with this. You've seen this happen a dozen times so far in this class. And then if you wanted to do the excited state, you just replace these G's with E's. The interesting thing that happens is when we move to 2 atoms, right? So let's move up a step to 2 wells. So we're going to go up to 2 atoms or 2 wells. There we go. We're going to move up to 2 atoms now. So you imagine that you've got a well here and a well here. And like we said earlier, they are separated by a distance a. That's our atomic spacing here. What ends up happening is that we now have 2 ground states, right? We've got a ground state for the left well, and we've got a ground state for the right well. So what we're going to do is we're going to call those phi 1 and phi 2. Now, we already have the function for that, right? We spent some time on that earlier this semester on the finite square well, where we got this phi g. It's this sort of modified sine or cosine thing. You remember we had to do this whole numerical approximation to figure out the wave number and everything. We're not going to go back and do that. We're just going to assume we know it, right? Because the thing you're interested in is the energy levels anyway. So you come over here. This means you'll have a ground state that is centered over here. So that's going to be x minus 1 times a, right? Because this thing is going to be located at 1 times a. Well, this thing's going to be located at 2 times a. So you'll have a phi ground state of x minus 2 times a, right? So what you've got for the first one is you've got it moved over a from the 0 point over here. So you can think of your 0 point as being over here, and then here's a distance a, and then here's another distance a. So it's going to be minus 2a. If we move up to 3 wells, we're going to have x minus 3a, then x minus 4a, etc. But if you just take this problem just for right now, this is a basis for the problem, right? This thing ends up being a complete basis to describe any state, which means any psi. You remember how to work with bases, right? From linear algebra or differential equations. Any psi I can write as a linear combination. So coefficient times phi 1 plus a coefficient times phi 2, right? So any of these states can be written as C1 times phi 1 plus C2 times phi 2. The only thing that's different are the C's, right? So maybe you've got an atom that's most likely to be located maybe you've got an electron that's most likely to be located near the left atom and not very likely to be located near the right atom. That means C1 would be heavier, C2 would be lighter, right? That's just, or maybe you've got an atom that's split 50-50. That would be 1 over root 2 and 1 over root 2. But what ends up happening, if you take this and solve this problem, and your textbook walks you through this, our textbook, Quantum Mechanics by David McIntyre, walks you through this in a pretty good kind of like bird's eye view. What you end up with, let me get, not ready for that slide yet. There we go. What you end up with are some energy levels. You end up with two energy levels, right? There's two basis states, so there have to be two energy levels. So your energy levels, they're both based around the ground state. One's going to be raised by an amount delta E. The other one's going to be lowered by an amount delta E. So your energy eigenvalues are either Eg plus a little bit or Eg minus a little bit. So it's like you're taking the ground state. Here's Eg. It's like you're taking that and splitting it. So you're either adding delta E or you are subtracting delta E. And you say, well, what's this delta E thing? Well, this Eg, it turns out, is an expectation value of your Hamiltonian if you use phi1 and phi1. It's the same thing if you use phi2 and phi2, right? Because this is the original ground state. The delta E is what you get if you mix the two states. So if you take your phi1, your phi for the left atom, and your phi for the right atom, if you mix those two, that's where you get delta E, right? So this term represents the interaction between the two wells or between the two atoms. And so this delta E, this splitting, is just this overlap term here. It also gets you the same answer if you swap 2 and 1. 1 and 2 and 2 and 1 will give you the same answer. So when we went from one atom, all right, so here's one atom, to two atoms, right? There's two atoms. When we went from one atom to two atoms, we went from one energy level to two energy levels. So this energy level split. So let's take a second on the in chat. Let me know, what do you think is going to happen to these two energy levels when we go from two atoms to three atoms? Tell me in chat, what do you think is going to happen? All right, haven't seen any answers come in yet. There's about a minute delay between what I say and what you hear, so we'll maybe just move along there. So when you went from one well to two wells, this one energy level split, what you're going to get when you go from 2 to 3 is that each of these energy levels are going to split. So this is going to split by an amount. This is going to split by an amount. So you can kind of think of a smaller delta E here, smaller delta E here. And what happens is if you keep doing this, let's get a new slide in here. Oh, don't tell me I've reached the maximum number of slides in Google Jamboard. Oh my goodness. Okay, apparently you can only, note to self, you can only have 20 frames in Google Jamboard. I wish they would have told me that. Anyway, what ends up happening is, fine, we'll go over to this one and I'll shrink this down till I need it. Nope, I didn't say rotate. I want you to shrink. Shrink. There we go. Okay, we'll save that for just a second. Good thing this is the last class. I'm out of frames on Jamboard. What you end up with, so you start out with the ground state. You split that up here. You split that next state here, you split that this way, right? So it's going to go like 2 to the number of atoms. Eventually what happens, you keep splitting these up. It's almost like you've got just a whole smearing of stuff you put together, right? So it's like you've got all these states split apart. They might as well be a continuous variable, right? So you end up with this limit where they're nearly continuous. So instead of calling these a level anymore, instead of calling this a level, we call this a band. And now here's the thing. You do that with the with the ground state. You can do that with the excited state. So you get the first excited state to split up, etc. You can get the second excited state to split up, the third excited state, etc. So you end up with these bands where the electron is allowed to sort of maneuver around in here however it wants. So it can jump up and down here easily. It can jump up and down here easily. But in between, you end up with this region called a gap. Right? So you have a band of energy levels, but then you end up with these areas called gaps. A gap is where it's very hard for the electron to jump. It's very hard for the electron to jump across the gap from one band to the next. Now, obviously, if the gap is narrower, it's easier. If they almost start to touch, it's easier. But if this gap is large, it's almost impossible for electrons to jump from one to the other. This is where we get this sort of, this is the most helpful picture I've ever found of this band gap structure. And so what you end up with are these bands. So here you might have a band with some gaps. Here you might have two bands that almost start to overlap. But the other thing you have to keep in mind is this sort of basic electron level called the Fermi energy. The Fermi energy is the energy level that you get out where if you fill up all the energy levels with all the electrons in the metal, this is the kind of top energy level that you get to. And basically all the interesting action happens at the Fermi level. So if I'm an electron, let's use red for now. If I'm an electron right here, it's really easy for me to jump up to here, right? It's easy for me to jump around the Fermi energy because there aren't any more electrons up here. See how these bands up here are white? That's because there aren't very many electrons up there. In fact, if it's completely white, there are no electrons up there. Whereas if I'm here down below the Fermi energy, I got to exert a lot more energy to get up there. And if I'm down here in this band, there's really no realistic way I'm going to make it up even to the Fermi energy, let alone past the Fermi energy. So we like to say that all the interesting physics happens around the Fermi level, happens around the Fermi energy here. And so the way you end up with different types of conductors is literally with these different types of band structures. So you might have your metal here, for example, that has a band that pretty much straddles the Fermi energy. You see how this band is kind of cut in half by the Fermi energy? So a nice, good, regular conductor is going to have a band centered around the Fermi energy, because then I can have electrons moving around here, easily jumping up and down across the Fermi energy. I can get those electrons to move. In a semi-metal, you might have a dip in the band, or you might have two bands that kind of partially overlap near the Fermi energy, where they can kind of squeeze through to move here, but it's not the easiest thing in the world. Go over to the right. When you have an insulator, you've got the Fermi energy straddling between two bands. So you have a band well below the Fermi energy and a band well above the Fermi energy. And so it's really hard for an electron to get from this band across the Fermi energy up to this band. When you're trying to cross the Fermi energy and a gap, that's a problem for the electrons. And then we have these things called semiconductors. You're just kind of looking at a little bit smaller of a gap. You still have a gap, but the gap is near the Fermi energy, right? So for example, for an N-type semiconductor, here you've got the empty band near the Fermi energy. For a p-type semiconductor, you've got the full band near the Fermi energy. And so that's why you've got one type where the electrons move easily, and you've got the other type where the holes move easily. So that's when we talk about electrons versus holes in a semiconductor. Let's see. So yeah, that's just a real brief introduction to kind of like how you visualize solid state, because really this stuff about bands and gaps explains how different materials behave differently. So this is one of the big achievements of quantum mechanics, is that we're able to explain how electrons behave in bulk like this. And really the way you study solid state is you just get more detailed than this, right? This is kind of the generic picture. You can imagine these shapes changing for each particular metal, right? So one metal is going to be have narrower gaps, and another metal is going to have wider gaps. They might have different shapes like this one over here. And so that's really what determines how a material behaves, is how the how the energy bands get determined using the same picture of wave functions and energy levels that we've been using the entire semester. So anyway, that brings our stream today to an end. I want to thank you all for your time and attention and for continuing through this really exciting class. This is one of my favorite classes to teach in our undergraduate program. And really happy to get to end on a high note here with a little bit of solid state. Looking forward to getting your last assignment and last project. Again, if you've got any questions on that, feel free to send me an email or stop by office hours later today and on Friday. All right, I wish you all well. Hope you stay healthy, and I hope to see you in the fall. Have a good day.